Great, ladies and gentlemen. So, what I've just shown you is a timeout transition. Please do not be fooled into thinking that timeout transitions are just for fixed values. You can actually draw the timeout value, the value in which you want them to leave. So when they come into normal glycemic, you can pick a timeout value by which they will go become diabetic from an arbitrary distribution. You could draw it from a custom distribution if you wanted to. You could draw it from one of these parametric distributions. The point is that the timeout transition is actually a very flexible transition type, although you might be fooled into thinking that it's just for fixed values. It's not. Okay? In other words, you can use it to impose arbitrary distributions involving the time spent in a given state. Okay. So I'm going to say for this transition here, I'm going to call it becoming diabetic. And you'll notice for transitions, by default, the name is not shown. I like to show names. They enhance transparency of models to stakeholders. So for this, I called it becoming diabetic. And I'm going to say show name. And now the name is shown. Astride the transition. Okay? Or bestride the transition. Okay. Yeah. Yes?
I just have a question. So when you're moving from the different health states, from normal glycemic to diabetic,
yeah.
Is there anywhere in the software that shows you the type of distributions this is coming from, kind of the probabilities and things like that, the point estimates on that?
So, okay, so I'm having trouble unpacking it, and I have a couple interpretations of the question. So those probabilities, or the probability distributions associated with so-called residence time, how long you spend in this state, are dictated by the transition types and the rules in terms of the values for those transition types. So let's suppose we have this becoming diabetic in a fixed value of 1 year. What that is telling us is that after exactly 1 year, before 1 year, you have no chance of leaving this transition. At 1 year, you're guaranteed to leave, and then you will, have left. Now, the residence time, so the residence time there would be, the residence time distribution would essentially be a spike at 1 year. In other words, we know everyone stays 1 year. Now, if I had drawn this from a distribution, let's say from a from a beta distribution or something, here with P and Q, it would the residence time in this state would be beta distributed with these parameters P and Q. And, I could impose other distributions. I could even use a custom distribution that we used yesterday to draw the value for how long I spend in the state from the custom distribution.
Could you specify it as a risk function at that point?
Well, the distribution, what this is giving is the residence time in that state. And that's going to be related to a hazard rate that would obtain over time. But I will show you a way right now where you can specify a hazard rate instead, a chance per unit time of leaving, which is another way to specify it. Besides, this is really specifying residence time, right?
Right, yeah.
And I could say here, as I think many people will realize, that the residence time is exponentially distributed, right? I could say it's an exponential distribution with lambda equal to, to 0.1. Yeah, so you go, if you want to see that, ladies and gentlemen, you could go up to this, you go up here, choose probability distribution, and we could set it to be an exponential distribution with a lambda of 0.1, in which case there would be a mean time of 10 years in that state. And I could say, okay, and it will insert that appropriately.
Where did you get to that probability?
So I did it by going up to this guy here, where it says choose probability distribution.
Oh, yeah.
Where's that?
Okay.
You have to have your cursor on something for it to be colored.
Winchell and Alan,
Got it.
could you help people find the probability chooser?
Yes, it does.
You found it?
Yep.
Where did you find it?
In the same spot as yours.
Oh, okay.
It's just not colored.
Yeah.
It's if you're not on an actual entry
Mm.
area, then you can't click.
Okay.
Yeah.
So you notice it's actually sampling from it to display this here. But, you know, I could, okay. So I could impose an exponential, but if I'm going to do that, the easier way is to specify it for exponentially distributed time, which is associated with like a fixed hazard rate of leaving. It's easier to do a rate transition, okay? By the way, you'll notice this thing has this value here. You don't want to leave, even though it's hidden when I do this, any logic remembers it, and sometimes it freaks out about things that aren't shown even. So I like to change this. So another way to specify this transition is using a hazard rate, a chance per unit time of leaving. Unit time is specified explicitly. So I could say I have a certain probability per unit time. It's not a probability, it's a probability per unit time, a density. And you notice it's point per year. So I could say a rate of 0.1 per year, in which case this will be, you know, an average time of 10 years in this state. Why do I say 10 years? Well, it's a factoid about exponentially distributed residence times. If you have a certain rate, hazard rate of leaving, of alpha, your average time before you leave, the average time is 1 over alpha. It's a mathematical fact that some of my lectures online you can find. I'll prove it.
So that rate is an exponential automatically, or is it?
So this is a hazard rate. And it implies, as a logical mathematical fact, that the residence time is exponentially distributed.
Okay.
But the key distinguishing feature of a hazard rate is that no matter how long you've been there, that same that hazard rate applies. So you know, I here could have been there in normal glycemia. I could have become diabetic. Could have been born yesterday, and I'll have a certain hazard rate of 0.1. Or I've been there for 100 years, and I have a hazard rate of 0.1 here. Okay, so a hazard rate is being specified here that is independent of how long you've been there. Now that hazard rate, somewhat confusingly, can change over time. So as I age, I could use a different hazard. As my characteristics change from other risk factors, they could change. And in fact, we're going to do that in just a few minutes, okay, with weight. That will be changing my hazard rate, right? Right now, it's going to be 0.1.
Just before we go on.
Yes.
While time is continuous.
Yes.
This would only have you updating at the 1 year?
Nope.
No.
No.
It would have,
It's going to actually, when you come in here, what's going to go on behind the scenes is that it's actually going to draw a value from an exponential. So there's this hazard rate going on, and it's going to actually draw the value from an exponential distribution, exponentially distributed residence time with a lambda of 0.1. It's going to determine when you would go out via this transition if nothing else happens first.
okay.
And that may occur, you know, in 3.235 years, or it may occur in 4.22 years. It's continuous time, okay? And it will occur at a certain time, and what that time is, it will draw from an exponential distribution when you come into the normal glycemic state. This will be very relevant in a little bit, hopefully before lunch, okay? Okay, so let's run the model. Let's have this be a rate transition with a rate of 0.1. Notice there's several others. Message transition we'll get to this afternoon. Agent arrival for movement, condition transition, etc. So ladies and gentlemen, let's go to the model. Let's run this thing. And now we see people changing over time to a diabetic status. with a hazard rate of 0.1. The average time to transition is 1 over 0.1, or 10 years. But some people transition sooner, some people transition later, okay? And a given person, if we go down to it, you'll notice this is counting down the time until this person becomes diabetic. See that? That's counting down. It's a reflection of the fact that drew that. Watch this. They're about to become diabetic. There, became diabetic. Game's up. Okay. Okay. So, ladies and gentlemen, here we have a rate transition. Hazard rates are one of the most useful ways to specify transitions within these models. It is continuous time. Okay, and that first model I showed you, that gestational diabetes model, you may remember back, just to connect this on. Don't feel you have to do this now, but I'm just going to go back to that model to reflect on this. You remember that within this model, our hazard rates, which are incidentally denoted in this sort of icon, these were specified in a way that is more sophisticated. For example, the fertility rate is specified in a way that is depending on their age here, although I think that would need to be recalculated in a way we'll talk about. This hazard rate of becoming dysglycemic depends on a hazard rate calculating using this formula, which depends on their current age, their birth weight in years, whether or not they're obese, whether or not they're overweight, their in utero exposure, and physical activity level, etc. Socioeconomic status, yeah. So this is a hazard rate that's being used here, and we know that it's a hazard rate because it's associated with this little icon that shows kind of an exponential distribution. Okay? So ladies and gentlemen, hazard rate or timeout. Those are two common ones for when you're going to have a transition and you want to inform it with some data. Okay? Okay, so let's talk then about getting in place some more texture. So we are going to add to this person. By the way, you'll notice one of my weaknesses of many is that I tend to be a little bit sloppy when building these models about aesthetics, about where to put things. Really, I should be careful lining variables up, lining parameters up, putting them in a nice area. Don't adopt my sloppy habits, okay? Okay, so ladies and gentlemen, we are going to add to this, so a state chart, mark my words, a state chart delineates transitions, so a set of categorical states, it delineates a set of possible categorical states a person can be in with respect to one particular condition. One particular concern, I should say. Concern. Okay? So here we have a concern involving diabetes. And we have these categories, normal glycemic and diabetic, and we'll use the state chart to characterize that categorical description and the transitions between them, these categories. If we have an aspect of a person's state that's not categorical, we'll often use a different thing, like a variable, and increment the variable over time, like the number of times they've been infected. We'll see that this afternoon probably. If we have an aspect of continuous state for the person, often we'll use a variable as a double precision value, and we will sometimes use stock and flows to determine it, otherwise we'll assign to it over time. These are different situations depending on what type of state we want to maintain. We'll use different constructs. So here we have one particular concern, to it diabetes, and we characterize it as having a set of categories and transitions between these categories. A state chart encodes the possible categories and the rules for transitioning between them. Next, let's add in from the palette a a weight state chart. Okay? Weight state chart. Okay? And the states here are normal and underweight. Now notice I am using this strange convention where I type a word and then wherever there's a new word I capitalize it. This is a convention, one of two conventions that is very common in software engineering. It is called camel case because it involves humps and sort of decreases. So that's one convention. Another one you could have used is underbars. And I will show you what that would look like. You could use something like this, normal and underweight, okay, like that. You will want to choose one of these conventions and stick by it, okay. So I'm going to choose this camel case convention for the sake of the boot camp. Now notice we can also enlarge these states so we can make it bigger if we want to have more space for it. Okay, great. Let me go recenter this. Boom. There we go. Normal and underweight, ladies and gentlemen. Good. Next, we are going to be adding in, ladies and gentlemen, a state that is called overweight. Okay. Great. And another state yet that is going to be called obese. Now, in some versions of this model, I've actually had two substates of obese. And state charts in any logic can include substates. You can have hierarchical state charts, able and disabled levels of obesity. I did this for some colleagues in Sydney and perhaps in Melbourne as well. So normal and underweight, and we're going to have weight change. I'm going to use my little arrow keys to sort of move these around. Maybe I'll put all the growing weights on the left, and we're going to have from overweight to obese, okay? Now, it's a good practice to name your transitions. So this will be called, this will be called becoming overweight, okay? Okay, and going from overweight to obese will be called becoming obese. Okay? Great. Okay. And ladies and gentlemen, okay. Great. I'm just looking at how to, okay, right. Okay, and next we're going to put in transitions in the other direction, from overweight to normal and underweight, and obese to overweight. Now, it could be argued that really what I want to do is not use a categorical description here, but rather a continuous weight, and I'm savvy to that, and on day 4 we'll do exactly that. We'll have a continuous weight as captured by stocks and flows. Okay, but for now we're going to have these transitions in this fashion. Okay, great. Okay, now because of time considerations, I am simplifying. This model here. So I just want to characterize these. These are all going to be hazards associated with this normal and underweight. And I've worked with, past longitudinal data where we've calculated these hazards. But these are going to be rate transitions rather than timeout transitions. And in the interest of bringing this example to a close by lunch, what we're going to do is we are going to set fixed values here, okay, for these quantities. Okay, so ladies and gentlemen, for normal and underweight to overweight, okay, I would like to specify here a per year hazard of 0.05. Now in general we'd specify these with parameters, and we might even specify those parameters in main, but 0.05. And overweight to obese, we're going to use 0.003. Okay, sorry, 0.03. Okay, so here 0.05, normal and underweight, becoming overweight. For overweight to obese, 0.03. For, I'm going to have this transition from obese to overweight called losing obesity, and the rate here is going to be 0.01 per year. And for this transition from overweight to normal and underweight, I'm going to have it losing overweight, and this is going to be a rate of 0.05. So let me go through those again. I realized I went through those quickly. For this one, going from normal to overweight, I called it becoming overweight, and the rate for me is 0.05. Okay. Overweight to obese, I called it becoming obese, and it's a rate of 0.03. Losing obesity, I called it, that was the one from obesity to overweight, and I had a rate of 0.01. And overweight, normal and underweight, a rate of 0.05. And I called it losing overweight. Okay, ladies and gentlemen. Great. So I'd like to now go see, is this, is the model incorporating these new dynamics? Okay. Now, one way to do that is to run the model and go down and manually inspect it. So let's build. We just completed a logical chunk of work. Let's build it. And the TAs stand ready. Okay. Okay. Any questions? Any issues with building it? Okay. So let's run this thing, and we should be able to run it. And one of the virtues of any logic is that you can characterize these structured transitions in a state chart with little or no code. I mean, we didn't write a lot of code to capture that state chart. A lot of packages out there, you would have to write quite a bit of code just to capture a state chart. Functionally, it's a state chart, and you don't even, when it's in code, you can't see it. You can't directly, visually inspect what's going on. You can't show it to stakeholders, and that's a big shortcoming. So here's somebody, ladies and gentlemen, that is in an overweight state right now. We could speed this up here, and they are changing states over time with respect to this, okay? Now, you'll notice, ladies and gentlemen, that there's certain information that was visible on the left-hand side here. For example, that's not visible here. And it's really useful information when this person will leave that state. And one of the issues is we've given too little space here. Excuse me. It's actually, that's not the operative issue here. The issue is we haven't shown the name. So with show name comes, it's actually displaying information about when it will transition. So for each of these transitions, I'm going to show the name. It's one more motivation for showing the name. For us, a big motivation is to be able to show the model to a stakeholder so they know what each transition represents. They can read the name and say, oh, that's someone becoming overweight or whatever. That's really attractive because often those stakeholders have tacit knowledge that you can elicit if they're interacting with the model. And in getting them to sort of be open to interacting with the model involves making them feel comfortable. When they look at it, they have some understanding of what's involved. So showing names is valuable, okay? So if we run this again, having shown those names, ladies and gentlemen, here we go. It will go down. Now we will see some information. This person in just over 20 years will become overweight. Okay, the countdown has begun. And here they go. Okay, and now they're going to become overweight. Boom. And now, okay, they lost weight before they became obese. So conceptually, what's going on is related to Vivian's question. When it entered the overweight state, it drew from an exponential distribution a value for when it would transition here and when it would transition here. And whichever one is going to occur first, it will do. Okay? This is actually quite a useful thing. I wish I didn't have to explain it at that level, but it will be useful in just a few minutes. Yes?
Just wondering if in this model everyone starts off as model and underweight.
Indeed. Indeed. And we're going to show a way that won't be the case. In fact, if there were interest right now, it would take about 5 minutes. I could divide people up so they start in different states. Would you like to do that? Okay. Okay. So for 10 minutes more, we could do it in a way that's most elegant, in which would allow drawing from a custom distribution in when we initialize the population, what fraction of people are in different states initially. Would you like to see that?
You need that.
Okay. Consider it done. Okay. Let's go do it. Okay. Great. Okay. So this is going to be a nice little nugget. So